Al secondo intervento del dottor Erik Andersson, vice direttore del Dipartimento delle Previsioni del Centro Europeo per le Previsioni meteorologiche a medio termine, che ci parlerà di centro meteorologico appunto come un esempio di come la tecnologia è utilizzata in meteorologia. Prego.
Thank you very much, Sergio. You will notice that I will not be speaking in Italian. Thank you also, Renata, for mentioning quite a few references to ECMWF and our products and how some of the models that you run are based on initial data from ECMWF. And also Francesca, before the coffee break this morning, had also several examples of products from ECMWF. So you might wonder then why I'm here. I'm Swedish and I work at the European Centre for Medium-Range Weather Forecasting in Reading in the UK. And this is a very good opportunity for me and for ECMWF to explain why we are building a compute centre in Bologna. So we're going to have our next big compute centre not on our own premises in Reading, but it's going to be operated remotely from Reading, and it's going to be based in Bologna. So I want to thank the organizers for this festival for inviting me to be here, and also we're very grateful to the Italian government and the regional government for a very good offer to provide us with a compute center, future compute center in Bologna. So really what I'm going to talk about in the next 30 minutes is the kind of thing that we are going to use this new compute center for. Why we have run out of space, we've run out of computing power, and we've run out of electricity power in our current site, and therefore we're moving our computer to Bologna. I present ECMWF as an example of how technology is used in meteorology. First of all, the importance of the work we do, all of us who are involved in meteorology, is captured in a recent report from WMO. It's in the Atlas of Mortality and Economic Losses from Weather, Climate and Water Extremes. We are active in all these areas. We do weather forecast, we monitor and map out the climate, recent climate through reanalysis, and we work on hydrological applications as well. And this report from WMO states that there were, in the period from 1970 to 2012, in a 42-year period, there were 8,000, more than 8,000, nearly 9,000 weather-related disasters around the world. There were millions, almost 2 million deaths caused by these events, and $2.4 trillion of economic losses. We have further evidence of the importance of the work we do, not only at ECMWF, but I mean the whole meteorological community. In a recent socioeconomic benefit study that we have conducted across Europe, and the economic benefits of further improved forecast is enormous. And it's really worth continuing investment and continuing to work on further improvement in weather forecasting for all these reasons. If we go back to the very beginning of ECMWF, we had this computer installed. This was in 1975, and it was a Cray. It looked like this. The current one is 2 compute clusters, and as I said, this is installed in Reading in the UK. This is one half of it. The second half is this one. This is the only Italian word in my whole presentation, or it's Latin, I suppose. Otherwise, it's going to be all in English. The difference between these 2 installations of computing power is 43 million times in terms of compute performance, and 180 million times more in terms of memory. What do we use this for? We use this for doing quite high resolution, I suppose, compared to the olden days, simulations of the weather across the globe. In these examples are for 10 days predictions of tropical cyclone tracks. And it's a very recent example and a very, very important one that got very widespread publication in not least American media. It was the Hurricane Irma that reached Category 5 and hit Florida. The interesting part about this is that the track was very, very predictable to start with. And that's what the graph on the left is showing. It shows a sort of colored band of the area of possible tracks. And this band is very narrow for many days. For 6-7 days is very narrow. And that means that the ensemble of forecasts that we run is indicating that all the 50 members are very close together in terms of forecast track. So during that whole period of evolution of this tropical cyclone, we can be quite sure that it's going to move from east to west across the Atlantic. 6 days later, on the 5th of September, the forecast is showing quite a different view. It shows a turn. It shows that this tropical cyclone at some point is going to make a right turn and go towards the north and hit America. And there, the spread between tracks is very much larger. So we know from this simulation that it's going to be very critical to predict exactly when and where this tropical cyclone is going to make its right turn. And that's then what the forecasters in America focused on. The National Hurricane Center in Miami used these forecasts and many others, and they got the message that it was going to be critical to predict when and where it was going to turn. And they used much higher resolution models, of course, to guide them as well. And then the rightmost plot is just 2 days later again. You can see that by now having assimilated observations for another 2 days, the tracks are again slightly less uncertain, and we're becoming more and more sure that the hurricane is going to hit Florida, but it's still uncertain whether it's going to go up the west side or the east side of the peninsula. So this example illustrates what you can do and how important it is to link every forecast with an estimate of uncertainty. This is what weather looked like back in the 80s, when the computer simulation was done with a 210-kilometer grid. If I move quickly through this, when we had 125-kilometer grid, it looked like this: 62-kilometer, 16, and currently we run our global model at 9-kilometer resolution. We run the ensemble at 18. What you can see, of course, when you go to 9 is that you're beginning to see the impacts of orography in the Alps and other parts. You're beginning to capture much better the intensity of weather events. And this is very important for our strategy, that even if you do medium range and longer forecasts, we want to be able to capture the possibility of something extreme occurring. So even if you don't know exactly when or exactly where something might happen, like strong convection or possibility for very damaging winds and wind gusts, we want to be able to say that there is a possibility that it will happen, and if it happens, we want to be able to say from the model how intense this event might be. And for that, it's very important to continue to improve resolution and improve the accuracy and realism of the models. A little bit more of history. We used to have craze for a long period of time. That was in the far left here. Then we had a period of Fujitsu machines from Japan. Then we had IBM for a period, and now we have had Cray for 6 years. Then the next one, you can see that the Cray contract runs up to 2020. That means that the next machine will be procured and installed here in Italy in 2000. 19 for operational use in 2020. I mean, it will be installed, well, it will, how is it now? We need to begin to install it the beginning of 2020 to have it operational by the third or fourth quarter of 2020, if I'm not mistaken. And through this history, if you map out the power, the sustained performance of the machine in a logarithmic scale against time, I think it starts in the early 80s and it goes all the way up to 2018, the current machine on the far right. And as I said, this is on a logarithmic scale. You can draw lines in here that are straight. So you can see that computing so far has delivered an exponential growth in capacity. And we're using it, and one of the main ways of using it is increasing the resolution. So you can work out here roughly how much more compute power you need in order to double the resolution. Of course, it's not only the resolution that costs compute power, it's also the realism of the model. The more physics, the more processes that you include, all of that also adds to the need of computing. HPC for numerical weather prediction is about performance, but more and more power consumption is becoming critical. You simply can't go far beyond the level of power consumption that we're already having. What's happening here? Anyway, I carry on. The power consumption is a problem, and we need a computer that's very reliable. We need software on this computer that is portable and that we can easily transfer to whatever computer turns out to be the most suitable for installation next time round. Another critical element is the time to solution. Simply, all that we do here is in a very tight schedule, and it needs to be done quickly. And as I said, energy, the requirement for energy is a limiting factor. Sustainability, we would like the electricity power to be as green as possible. We need also 24/7 support, and we need a machine that will, if it falls over, if it has a problem, that it can easily be recovered and we can quickly be operational again. This is about the forecast production workflow. It starts with data acquisition, bringing the observations in. We run the forecast on the computer. We run the product generation. We then produce the products. They need to go out. They need to go out to all our users. That step is called dissemination, and it basically relies on the internet to deliver those products out to our users. But we also have an RMDCN. This is a regional meteorological network that ECMWF operates for WMO. Thank you. I don't know what's going on. And the third element that we need for the products is the archive, a large meteorological data archive and a data handling system. I'm going through this in a bit of detail because the way we are envisaging the compute center in Italy, in Bologna, is that all of these steps will be run here. Everything from data acquisition all the way through to the dissemination will be part of the Bologna operation. That means that we will need the aerials to receive satellite data on the roof of the new compute center, and all the way through to the powerful networks that we need to deliver the data to our to the weather services around Europe and other users of our forecasts. If we look ahead to, this is a few years away yet, so we have to at the same time think, how will things develop? How much different will things be in years ahead? Now that we build a new data center, what are the challenges going to be for the kind of model we may need to run in 5 or 10 years' time? So if we're looking at the figures for current data acquisition and the one that we may need 5 or 10 years down the line, we think that this is going to possibly evolve by a factor 10. So the F there is a factor 10 in the amount of observations we will need to handle. If we look at the forecast itself, you will see that the figures there are quite staggering. There are some characteristics of the model that you can see there. The number of grid points, the number of vertical levels, the number of prognostic variables, and the number of members in the ensemble. You will see that you can think of evolutions of the forecast model, but all of those numbers will increase dramatically. And if you multiply them through, you get frightening numbers of a model that may be 2,000 times more compute hungry than the one we have at the current time. If you go through similar projections for other parts of this chain, you will see that they will all increase a lot, but not as much as the computer model itself. The archive is already challenging, and if it's 100 times bigger, that will be a problem as well. But this analysis shows that it's really the forecast model that is the main power-hungry element of the production chain. So how do we tackle this for the future? We need to make preparations now, and we need to put the research efforts into place now that we need to go forward. So we are focusing a lot in our strategy, in our research strategy, for improved realism in the model, for improved coupling between physics and dynamics, continue to quantify uncertainty in all elements of the model and the observations. We want to cover additional components of the Earth system and invest in novel numerical methods that will be more efficient so that we can bring down this factor of 2,000 to a more manageable level. Another line of attack, if you like, is to work with many European partners in computing and software development to work on scalable codes, making our and other people's numerical codes more scalable and more efficient for running on large computers, and also to maximize the energy efficiency of our codes. Right, so that sort of concludes the part of the talk that focused on the compute element. Now I have just a couple of slides, very few, on some of our most important products. The first one I show ties in with the most important strategic element of ECMWF, that we want to focus on extreme weather. And the most popular, most successful products in that area that we have is the Extreme Forecast Index. Many of you are very familiar with it, but it's a measure of how different the current ensemble forecast is to the model climate in that same location for that same time of the year. It is computed from a accumulated distribution function, which is at the lower right illustration. In that figure, you see as a black curve the model climate. So you derive that from running the current model on many past events for the same time of year, but for past years. So we run the current model for the past 30 years or so in order to derive that curve. Then we draw the cumulative distribution function of the current ensemble run, and the ensemble run for the past 10 days in different colors. And that shows you how different, or how different the predicted weather for this coming week or so is from the model climate. And from that, we compute the index, which is an index between -1 and 1. And if it's 1, it shows that the ensemble is completely outside the model climate. The example here is of a windstorm that hit Northern Europe recently, and it immediately draws the user's attention to those parts of Europe where something extreme may happen. This is a product that works very well in the medium range, and we're working on extending it to second and third week of the forecast. See how that goes. The normal product for the second and third week of our forecast is simply a monthly mean anomalies, weekly mean anomalies. Here's an example of a heat wave over parts of Europe, Western Europe. And in this case, it was well forecast, sort of 10 days ahead, week and a half. But if you go further into forecast, 2.5 weeks, it was very poorly forecast. And that's basically where we are, that even these large-scale events, they are often, we see that there is a predictive signal up to 2 weeks in advance, but further on, we're still struggling and improvements need to be made. So we are focusing a lot on extending the predictability into the second and third week of forecast. Finally, on the seasonal range, the most important part to predict is the sea surface temperature in the tropical Pacific. And that's one of the products we have there. And from that, of course, we want the seasonal forecast system to predict the downstream impact of such events. And that's what the seasonal forecast system does. I also want to show briefly some work that we do specifically for the European Commission, where we are working on Copernicus, where we are responsible for atmospheric monitoring. And there we are simulating and predicting the atmospheric composition. For example, aerosols from wildfires, aerosol from Saharan dust, and also other chemicals constituents of the atmosphere. Also funded by the European Commission is the Climate Change Service, where perhaps the most important element is the climate monitoring through reanalysis. At the moment, the reanalysis that we are producing is called ERA 5. We're also doing EU-funded work on flood forecasting, and the new development there is called GLOFAS, a global flood awareness system for the main river basins around the world. I'm going to show a couple of scores of results, just a couple. Many of you have seen this one. For each time range of forecast, it shows the northern hemisphere at the top line and the southern hemisphere as the lower line. And the gap in between the two, the difference between northern and southern hemisphere is colored in blue for the 3-day forecasts, in red for the 5-day forecasts, green for the 7-day, and yellow for the 10-day forecasts. The first thing you see here is that the difference in forecast skill between the two hemispheres suddenly reduced a lot in the late 90s and into the early 2000s. That was because we got so much more information out of the available satellite observations at that time by adopting the 4D VAR data simulation system and other improvements. Since then, the forecast skill in the two hemispheres has been very, very similar. The other thing you see is that the forecast skill continues to improve with some ups and downs. I'll come back to that in a minute. Compared to other centers, we have a good lead on this one. It's ECMWF compared to UK Met Office, Japan, Canada, and the US. Here we're zooming in a bit more, and we've added a couple of curves from forecasts run from reanalysis. the reason for doing that is that in that case, we are using the same forecast system throughout the whole period, and you would think that the skill would be almost constant. And that's what you can see from the interim in dotted, that basically throughout the period, the skill with that frozen system is fairly constant. But there are some ups and downs, and those ups and downs reflect the predictability of the atmosphere in those years. And we use that to help us explain why sometimes our forecast skill scores seem to go up and down, even if we haven't changed our model. Or sometimes when we made a good change to the model, the skill scores still go down. And it's because the atmospheric predictability varies on these timescales. So you see that there was an anomalously high level of performance in 2010 and 2011. And by running the forecast from the frozen era interim system, we can be sure that that was actually not an indication of improved model, but it was a state of the atmosphere that made it more predictable. The more recent years, we have seen a very strong improvement, but by looking at era 5, we see that some of that improvement also occurred in the frozen system, which means that part of that improvement is due to predictability of the atmosphere, and part of it is due to improved scale of the model. We have fairly recent new strategy. We have a strategy that was recently adopted by our council. It's a strategy to the year 2025. So this ties in very well with the period for which we are now going to procure our next computer. So in the period of the next computer, we need to be able to realize some of the goals, the main important goals of the strategy. And those are formulated on 3 pillars: Earth system modeling and analysis, simply meaning that more components of the Earth system need to be addressed by the model: the ocean, the sea ice, the land surface, and so on. We want to work towards an ensemble, a global ensemble with 5-kilometer resolution, and we need to address the issue of scalability across the whole NWP chain to make such a model affordable. So in a nutshell, these are the 3 elements of really main important work for us going forward. This is to illustrate the Earth system modeling approach. The kind of processes that many of these are already included in the model, but others remain to be added, particularly to do with the sea ice, glaciers. We don't have complete coupling to the ocean yet, but it's coming, and we need to improve the treatment of the land surface. We are working, and we are almost ready to start using a model that's coupled to the ocean also for the high-resolution model. The ensemble has been coupled to the ocean for a while, and we are now taking one further step and also coupling the high-resolution model to an ocean. We couldn't do that before because it was very costly, but we worked on the ocean model, make it more affordable, not only us, but with our partners. And this shows some results from tests with this model that we are going to introduce at the beginning of next year. And it shows in this hatched red shading that particularly in the tropics, the coupling to the ocean makes forecast skill improve. And we think that by improving in the tropics, we will also, in the long run, see improvements at mid-latitudes and in Europe. It so happens that this year we're celebrating 3 anniversaries. So towards the end of this year, we're going to have some seminars at the center, and we're going to have some articles to celebrate the fact that we have now been doing ensemble prediction for 25 years. We've been doing Fordivar for 20 years, and we've been doing seasonal forecast for 20 years. Finally, this is the artist's impression of what the computer hall in Bologna is going to look like. I haven't been there myself. I understand that it's a former factory, and it's going to be refurbished and it's going to be turned into a computer hall for our next computer. So, thank you very much. That's all I had.
Grazie per il suo interessante intervento e volevo sollecitare qualche domanda da parte del pubblico, se c'è, per dei chiarimenti ulteriori.
Thank you for the very clear presentation. My name is Frustacci from Fondazione Meteo Duomo. You showed us how large is the economic loss because of weather disaster in the world, and also showed us how increasing is the resolution, spatial resolution of the model. When do you think, my question is, when do you think, or how do you think that the ECMWF model will cope with urban meteorology effects such as urban heat island, for example? Also because most part of the world population is now living in urbanized situation. Thank you.
Yes, you're right. Our model is still a global model, and its resolution is still not going to be competitive with what you can do at national level with limited area models. As we heard before, that the regional weather services run very much higher resolution models than we can do. And I think even in this time period of 5 to 10 years ahead in time, we will still need very high resolution models, not least for this kind of problem that you mentioned, the urban meteorology. We are currently not even working on the urban problem. I think it's still a problem that needs to be addressed, or is being addressed in limited area models.
Qualcun altro, qualche richiesta, qualche altra curiosità? Bene, allora ringraziamo il dottor Andersson.
Thank you.
Grazie.
Thank you.
Soltanto un paio di avvisi prima della pausa. Volevo avvisarvi che durante la pausa, diciamo, dedicata al pranzo, c'è la possibilità di assistere a una presentazione che verrà svolta in aula meeting, quindi sopra le scale, ed è offerta da ENAV su un nuovo sistema di data logger. Alle ore 13:30 la trovate sul libretto, ma si svolgerà in aula meeting. I lavori qui riprendono alle 14:30 con l'intervento del dottor Andrea Piazza. 2 avvisi operativi. Alla vostra sinistra, uscendo, trovate la medaglia del Presidente della Repubblica, e chi vuole aderire all'appello al Presidente affinché prima o poi ci venga a trovare a Rovereto è invitato a farlo, e più siamo, più probabilmente è probabile che questo venga preso almeno in considerazione. Il secondo avviso, un po' più ristretto, riguarda i soci AISAM, l'Associazione Italiana di Scienze dell'Atmosfera e Meteorologia, che domani avranno l'assemblea qui. Alle ore 13 di domani ci sarà la possibilità di visitare i locali che Trentino Sviluppo ha offerto per la sede AISAM, e quindi tutti i soci che sono interessati a vederli si ritrovino alle ore 13 allo stand ENAV nell'atrio. E a questo punto colgo l'occasione per dare il benvenuto al colonnello Vittorio Villasmunta, che è reduce da un infortunio di salute, troviamo in piena forma qui con noi. Ci vediamo alle 14:30 puntuali per la relazione di Andrea Piazza. Grazie.
Hai volato, Vittorio.
Thank you so much. I understand you want the map. I'm sorry.
I was worried that it came from my